Brownian motion, the seemingly random dance of particles in a fluid, unveils the profound hidden order of the microscopic world, echoing the ceaseless energy that shapes our universe.
Brownian motion can be applied to economics in two respects. Underlies an important part of stochastic finance, which includes the pricing of risky assets such as stock prices, bonds, and exchange rates. These models draw an analogy between economic transactions and particle interactions in physical systems. It also plays a key role in econometrics, especially in the distribution theory underlying test statistics for a unit root. These models draw an analogy between economic transactions and particle interactions in physical systems. In kinetic energy models, individuals are modeled as particles, and their wealth or income is akin to the energy of these particles. Economics transactions are modeled as exchanges of wealth between pairs of agents, similar to the energy exchanges in particle collisions. There are two main types of kinetic exchange models. A fixed fraction is where a fixed percentage of the poorer agent's wealth is exchanged, and a stochastic fraction, where the fraction of wealth is randomly determined. So how can Brownian motion actually be applied? In Brownian motion, particles undergo random walks due to collisions with fluid molecules. Similarly, in KEMs, agents' wealth undergoes a type of random walk due to stochastic economic transactions. A stochastic process is defined as having a random probability distribution or pattern that can be analysed statistically but not predicted precisely. Both systems can be described by stochastic processes. Brownian motion is a continuous time stochastic process, while KEMs often use discrete time models. The random wealth exchanges in KEMs can be modelled using techniques similar to those in Brownian motion, such as the Langevin or Fokker-Planck equations. Just as particles in Brownian motion reach a thermal equilibrium with a Maxwell-Boltzmann distribution, wealth distributions in KEMs reach an economic equilibrium. The resulting wealth distribution can be analysed using tools from statistical mechanics. Now we're going to consider how we can actually model Brownian motion using statistics. We're now going to consider a filtered probability space with outcomes and filtration of F and probability space P. So here we have from the interval 0 to time, represented by big T, we have a set of real outcomes. Brownian motion always has an initial value of 0 with independent increments, having a Gaussian or normal distribution on those increments, and it has continuous sample paths. We'll now go on to explain each of those properties below. Let's start off with the most simple example that we can have, a symmetric random walk. A random walk can be pictured in the following way. Say that we have successive coin tosses represented by omega, where each of those omega values is either a heads or a tails. The nth outcome is the nth outcome of that toss. This is going to be represented by this xj variable. So it's going to take on 1 if our outcome is a head, and it's going to take on -1 if an outcome is a tail. We now define a process with m0 equal to 0. mk is going to be the summation along all those possible coin toss paths, and that's going to hold for k tosses. So effectively, we have a random walk that can either go up 1 or down 1, and we can see this sum over the paths. If we were going to graph this, it would look like the following. Let's now look at the properties of the above graph and symmetric random walks. So the increments between time periods are independent. This means E of x equals 0, and the variance of adjacent time periods is equal to the difference in time, or distance. The martingale properties mean that conditional expectation of the next value is where we are now. The filtration holds all the info up to time k, so given that all the info up to time k, the expectation of ml is equal to mk. The quadratic variation of m with respect to m over k time steps is worked out by taking the independence time steps, squaring them, and then summing them over a path-by-path basis. The distance in the increment between those steps is equal to k. Now we're going to consider a scaled symmetric random walk. To approximate Brownian motion, we can speed up time and scale down step size. So for each time step, we can take 10 increments for each year to give 100 different time steps. This should provide the graph below. So it still holds the same properties as discussed above. So variance at a particular point along all those paths is equal to the time period. We can now think of this in terms of the limit of the binomial distribution. We still count heads going up by 1, tails down by -1, but scaled with whatever n value we are using. So as n increases, the binomial distribution converges to a normal distribution with variance t. We can use the combinations formula to work out what the binomial probability is for each outcome and a lambda function to work out each of these probabilistic outcomes. It's then graphed in the histogram shown. The black line is the normal distribution. What we are now effectively saying is that if we take the limit as n tends to infinity, we get a normal distribution with e of x equaling 0 and variance of t. The next step entails sampling from this normal distribution. What we find is that e of x equals 0 and variance is the actual time difference. From this, the next step was to create a simulation to experiment modelling this. With some minor adjustments to the simulation, it can be modelled as a stock starting at 100 and shown as its change over a year. The volatility of this stock was defined as sigma and given the value of 0.3. The coloured lines represent different possible outcomes of a stock price as it goes across a year.